So when a force is acting on a particle, sometimes we call this a collision. Now, next week we're going to go more into what a collision is and how we have this thing called conservation of momentum during a collision. However, before we talk about that, we're going to talk about what a series of collision is and how those particles that are colliding with an object in a series are going to change the momentum of the object to have an impulse on that object. So for a series of collisions, so in this case, we have a series of identical repeated collisions on a target. So something like a bunch of BBs hitting a target or something like that in succession, in rapid succession. So we want an average force, F average, during the large number of collisions. And so, of course, we know that impulse is equal to change in momentum. But in this case, since we have a large number of collisions here that are causing an impulse on the object, we put this term N in here. So this delta P is just the change in momentum of each projectile due to the collision with the target. Our N is the number of projectiles that are hitting the target. And then J here is the resulting impulse on the target. So this is what the target is feeling. So that negative there is there because the impulse of the target has an opposite direction than the impulse of the projectile. So if we're finding J, the impulse on the projectile, we would take the negative away. But of course, since we know from Newton's third law that every action has an equal and opposite reaction, the same impulse on those projectiles all added up together will be also the impulse on the target, but in an opposite direction, which is why we have that negative there. So in order to find the average force on the target, we know that force is equal to impulse divided by time. And then, of course, impulse we saw on the last slide will be equal to the negative n number of particles times the change in momentum. So we plug that in for J here, and we end up getting negative n over t times our change in momentum. And then we get just plugging in mass times the change in velocity for our delta P, we end up getting this right here. So negative n over t, which is the rate at which the particles collide with the target, and then times the mass times the change in velocity. So that's a change in velocity of the projectiles in that case. Now, just some little points here. We can have different types of changes in velocity. Sometimes if the projectiles just stop upon impact, that means that the final velocity is zero. So our change in velocity is equal to final velocity minus initial velocity. If the projectiles stop, then final velocity is just zero in this case. So we end up getting zero minus v initial velocity. So we just end up getting that delta v is just a negative initial velocity. And then if the projectiles bounce off, so they're rebounding directly backward from the target with no change in speed, then our final velocity is equal to a negative initial velocity. So we end up getting our delta V is equal to final minus initial, and our final velocity is negative initial velocity and then minus initial velocity. So we get negative 2 times the initial velocity. Now, in the time interval delta t, an amount of mass, which we can call delta m, can be equal to n times m. So the number of particles times the mass of each particle. And those are what is colliding with the target. So we can just put in place for n up here, because we know that we had n here and then we had m here. So n times m will just be equal to delta